So now what we will discuss is, we will discuss 3D representation, like how I can represent a point or a pixel in 3D space. So that we call it like the 3D representation. So two major families of 3D representations are there. Two major families of 3D representations are there. So that is explicit and implicit. So the idea is that if I want to represent a pixel in 3D space, I can go for a, and not only pixel, it can be scene also. Like, and what is a scene? Collection of pixel is scene. So how I can represent a scene in 3D space? So in order to represent the scene in a 3D space, I can go with explicit representation. I can go with implicit representation. So we'll discuss both of these things. So first, let us focus on explicit representation. So explicit representations, explicit 3D representations. What we do is that here we make use of direct geometric structures. So in order to represent a 3D scene in 3D space, we make use of geometric structures like 3D geometric structures, and we combine those geometric structures to represent a scene in space. So we define a shape using discrete geometric elements, and that geometric elements can be points, edges, or triangles. And in implicit representation, what we do is that instead of making use of geometric structures, we make use of continuous functions. So in implicit representations, continuous functions learned by neural networks. So we will represent a scene using a continuous function. There we will be having a continuous function. That function, whatever input you will give, it will give the output. Like you will give a coordinate as input, that okay, and it will give the output like, okay, what will be the pixel in that coordinate. In that way, so I have a function, it can generate, it can represent a 3D scene. So if this is the coordinate, this is how the pixel will look like in the 3D space, like that. So that is the implicit representation in the form of a continuous function. So explicit representation, we saw that, okay, direct geometric structure. So three ways are there. We can make use of point clouds. Point clouds. As you can see here, point clouds. So 3D points. So it is basically set of points in 3D space. Each point stores position plus color. So we have set of points in 3D space. Every point will store the position, the coordinate, and the color. So a collection of unconnected dots in 3D space. So each dot has a position coordinate, that is the XYZ, and color coordinate, that is RGB. Now if we talk about the pros, it is simple, fast to render, and easy to visualize. So the idea is that I want to represent a scene in 3D space. I can make use of point clouds. I can represent a scene in the form of point clouds. So if I make use of point clouds, it is very simple, fast to render, and easy to visualize. But what are the limitations of this approach? No surface connectivity. So in point cloud, the points are disconnected. So it is discrete, it is not continuous. So no surface connectivity is there. Sparse appearance, hard to represent smooth surfaces. So that's a drawback of point clouds. If we talk about second way of explicit representation, that is voxel grids. Now, what are these voxel grids? Let us look at. So voxels are basically 3D equivalent of pixels. Like they are basically cubes, and these cubes are like 3D pixels. So in voxel grids, we make use of 3D pixels that are cube. So we divide the space into small cubes. So voxel grid means 3D space, we divide it into small cubes, and we fill that cube with the color and with the intensity to generate a scene in the 3D space. So that is the voxel grid. So each cube is either occupied or it can be empty based on the representation. So we can represent a scene in the space using voxel grid. Now, what are the pros? Uniform representation, easy collision or volume queries. And what are the challenges? Okay, so here the main challenge is the memory, because memory grows cubically, very expensive at high resolution, and mostly empty space. So voxel grid is a very good approach of representing 3D scenes, but it is like it needs lots of memory. As we keep on increasing the cubes, the memory will keep on increasing. It is very expensive at high resolution. Then we have polygon mesh. So we have in polygon mesh, like we will be having vertices, edges, and faces. So polygon mesh, the idea is that we will be having vertices like the point cloud. Then we will connect those vertices with edges, and then we will apply the texture. We call it the faces. So that's what will give us the polygon mesh. So vertices are connected by edges to form faces, usually triangles. So this is also one of the way of representing like 3D representation. So 3D representation, we can have point clouds, we can have voxel grids, we can have polygon meshes. Now, what are the advantages of polygon meshes? Like the pros, it is the industry standard. Like industry, polygon mesh is used. Why voxel grid is not used? Because it can take lots of memory, editable geometry, and real-time rendering. And what are the cons? Okay, hard to reconstruct automatically. Now, the idea is that polygon mesh, it is like the topology is fixed. Changing the topology, like punching a hole in a sphere, breaks the list of vertices and require complex remeshing algorithm. Like we cannot reconstruct it automatically. Any change in the topology, we have to rerun the meshing algorithm. It requires complex optimization, and it is not differentiable. So it is difficult for neural training. It's difficult for neural training. Okay, now we will discuss optimization problem of explicit representation. Optimization problem of explicit representations. So why explicit structures struggle in deep learning? So the optimization problem. See, basically we cannot do the deep learning with explicit representation. Once again, I'll tell you what it means. See, the idea is that we represented a scene in 3D, like a 3D representation we did using explicit representation. So 3D representation we can do either using point clouds or voxel grids or polygon meshes. Now the problem is that they are discrete in nature, and because of that, gradient descent we cannot do, because optimization using AI, especially that deep learning, that we cannot do because that involves gradient descent. And gradient descent, it requires continuous parameters, because if it is continuous, then only it will be differentiable. And unfortunately, explicit representation, it is discontinuous, it is discrete, and hence gradient descent we cannot apply here. And that is the optimization problem of explicit representation. So if you represent a 3D scene using explicit representation, you cannot use neural networks to optimize it. And one more disadvantage, like the optimization problem, is meshes and voxels. They have discrete topology, hard to optimize shape directly. So the key takeaway for us is that explicit geometry is great for rendering. So for real-time rendering, it is very good. Like you can represent, but it is difficult to learn automatically. And what is the meaning of learning? See, the idea is that if I want that, okay, any change, it should automatically adapt without we running the algorithm. That is not possible with explicit geometry, explicit representation. Because in explicit representation, any change in the topology, we have to rerun the mesh algorithm. It cannot adapt in real time. It cannot adapt in real time. And that is the very big drawback, because now we are living in a world of AI, wherein software systems, they're adapting based on the uncertainties of the real world. It is adapting. But explicit representations, they cannot adapt. A small change in the shape, we have to rerun the mesh algorithm to fill the space. And that too in the same way. So that's the problem. So this is like the point cloud. Point cloud looks like this. So as we can see in the, like we generated a 3D scene. So it is like a 3D representation wherein we have points, and these points are not connected with each other, discrete points, disconnected points. And this is the point cloud. This is the voxel, voxel grids. As we can see the 3D space, we divided it into cubes, and we are filling the cubes to represent a 3D representation we can see. And this is the mesh, polygon mesh, wherein we have vertices connected with edges forming faces like the triangles. Okay, now we'll discuss the implicit representation. So see, in implicit representation, a scene is represented as a continuous mathematical function rather than discrete geometry. This makes it very powerful. So the idea is that I want to go for a 3D representation. I want to represent an object in 3D space, or I want to create a scene in 3D space. So what I can do is that I can derive a mathematical function which is continuous in nature. So a continuous mathematical function can represent a 3D scene, and that is something very powerful. Now, how it will be done, all that we'll get an idea, but now you just feel the power of mathematical functions, that they can also represent 3D scenes. So we can have continuous mathematical functions which can represent 3D scenes, and that is the implicit representation. So we already saw that, like if you represent using geometry, then it has to be discrete. But if you represent using a mathematical function, then it will be continuous. And since it is continuous, it can adapt in the real time because it can learn. We can apply neural networks here. Okay, so before going there, we will get more idea about how, like what that mathematical function will look like. So the general form of the mathematical function is, this is very important, like the mathematical function, it will take the coordinate like x, y, z of a point, like this point. So you just have to give x, y, z coordinates for that point, and the function will return the property. And that property will be basically, density. Like for that xyz coordinate, what will be the density, what will be the color, what will be the distance to surface, and what will be the radiance, the light. So now it's very clear that, okay, we have a continuous mathematical function which is representing a 3D space. What I have to do, I have to just query it. I have to just give it coordinates. Okay, this is the coordinate xyz. It will give me, for that coordinate, whatever the pixel will be there in that coordinate, it will tell that, okay, this should be the density of that pixel, this should be the color, this should be the distance to the surface, and this should be the radiance. And in this way, I can construct that pixel. And in this way, I can just keep on giving it the points and keep on generating the pixels. And I will be able to generate a continuous surface. So that is the implicit representation. Now we can look at one example of such continuous mathematical function which can represent a 3D space, and that is signed distance functions. Now what are these signed distance functions? Let us understand that. So function returning distance from any point to the nearest surface. So signed distance function, what they do is that you give it a point and it will return the nearest the distance of the given point to the nearest surface, that it will return along with the sign. So if the sign is positive, it means whatever xyz I gave, it is outside the nearest surface. If the sign is negative, then whatever point I gave, it is inside the nearest surface. And if it is 0, it means whatever point I gave, it is exactly on the surface. So now it's very clear that we have something called a signed distance function. Now how exactly it looks like, all that we will not discuss now, but you should get an idea that okay, we have continuous mathematical functions which can represent 3D space, 3D scenes, and we one of that is signed distance function. Now this signed distance function, what it is exactly, the mathematical function we are not discussing, we are discussing its nature. What it can do is that whatever point you give it xyz, it will give the distance of that point from the nearest surface, and that distance can be positive, negative, or 0. If it is positive, it means the point is outside the nearest surface, negative means the point is inside the nearest surface, and 0 means it is on the surface. So here we can see that this is the distance to the surface. This is the distance to the surface. Now, definitely advantages if we talk about, since it is continuous in nature, smooth surfaces we can get, compact representation, like see, because see mathematical functions now, they are like small formulas and they are differentiable, like they can be optimized. Now one more way of neural like implicit representation. So implicit representation means representing a 3D scene with a continuous mathematical function. So one of the way is like signed distance function. There is another way, that is the neural implicit fields. We can make use of something called as neural implicit fields. So in neural implicit fields, we make use of neural networks to represent function. So here the function, the mathematical function will not be in the form of any formula, rather it will be a neural network itself. So the continuous mathematical function will be a neural network wherein we will be giving the coordinates, 3D coordinate xyz, the input coordinate, to the neural network itself, and the neural network will output that okay, for that coordinate, for that point, the density, the color, the distance, it will output, and also the radiance. So the properties for that coordinate it will output. So neural network will output. And how it works is that, and see, this is actually more feasible because see, the idea is that now I'll share very good insight with you. I'll share very good insight with you. See, the idea is that for different representation, the mathematical function will change. We cannot have a single mathematical function which can represent all different 3D representation. Let us suppose in a 3D scene, I have a particular set of objects, like I have a 3D representation, a 3D scene of a cricket match. I have a like a cricket playground. Now the mathematical representation will be very different from that of a football ground. So the problem with then so the problem is that if we go with maths, like the formula, if we go with the formula, it will be very tough for us. Why it will be tough? Because for every scene we will end up like researching and discovering that formula, mathematical formula, that okay, this is that mathematical formula which is representing this. And we should the easy way for that is that let neural networks learn that formula for us, and that is what neural networks are good in. They can decode the underlying mathematical function. They will learn that for us. So how we train the model? You are already aware of supervised learning. In supervised learning, what we do is that okay, this is the point and these are the properties for that point. So with this, like if we give it, if I give the neural network this information that okay, this is the point, this is the properties, this is the point, this is the property, this is the point, this is the property, and if I give millions of points along with the properties, it will learn the underlying mathematical formula. And once I have that underlying mathematical formula, I have trained a neural network which is representing a 3D scene. And the best thing about this neural network is that we can even optimize it further. Any changes in the condition, we can retrain it, we can fine tune it. Very easy, compact representation it is. So the network, it memorizes the object. To see the object, you must shoot rays through the volume and query the network at millions of points to accumulate the image. So once we have this trained neural network in place, we just have to give it the coordinates and it will give us the properties of that coordinate, and we just have to render those properties and we will create a scene we can create it. It will be time taking because neural network, every point you are passing it, it will take some time to render. It will take some time. Like in real time, we cannot generate the scene, but we can generate the 3D scene. And the best thing about this is that, okay, you want to represent a new scene. You can create a new neural network. You can train a new neural network. So you can have different neural networks for different scenes. So every neural network will represent a different scene. So it can be very interesting. So that's the idea. Now, the benefits of this approach: neural implicit fields, continuous resolution. So, yeah, so the idea is that since, so we are talking about benefits of implicit representation as whole, like it includes a neural implicit field also, signed distance field also. Since it is continuous in nature, we can zoom in, zoom out. It is memory efficient because now we don't need large memory to store information. Rather, it is stored in the form of neural networks and some mathematical functions. And it is learnable via gradient descent. So that's the idea.